Good? Okay. Well, hello there, Mr. Guyette and the rest of class. It is probably like 10 o'clock right now, so if I flub a couple words, don't worry about it. So, to start off our Rube Goldberg machine, we have this lovely homemade spring from a notebook, cord, and some other stuff that is going to launch this marble and hit the parabola, which will send it down this hole. Now, if you look below, there's a tube here, and this tube leads down, and there will be a weight in here, and what's going to happen is the marble's extra weight is going to force the weight out of the tube, and this is going to cause this little teeter-totter to kind of come up, and when that comes up, this string is going to create more lack in it, which will then have this weight drop onto the remote control for this little lovely Tonka truck carrying a mooing cow.
It's an elephant.
It's an elephant. So then it's going to go on the track all the way up here, and it's going to do its business and then hit a couple dominoes. And then those dominoes are going to hit some more dominoes, which hit some more dominoes, and the whole thing just kind of continues. And then it's going to hit this lovely colorful marble, which will come running down this track to hit the power strip. And when it hits the power strip, it's going to turn on this beautiful oscillating fan. When this oscillating fan does its job and oscillates, it will pull that red remote control, which will then cause the fire truck to go on an emergency and send some marbles down a very ugly, I don't remember what this is called. Plinko board. This Plinko board will then come and send marbles down this nice little tubey thing, down some other tubes, into a cup. Now if you see on the cup, there's some strings that are tied to a pair of scissors. Those are KitchenAid scissors, good quality scissors we got going here. That will then cut the string for the catapult, which will launch another marble all the way over to here. And from there, what will happen is the marble is going to go and roll down this ramp to this inclined plane, more formally. And then if you look really, really close underneath, what's going to happen is the marble should roll down this way and come down and hit this power strip.
You're far less limber than you used to be. I can hear you creaking as you're wandering. Make a move from city to city, but I can't take it in, 'cause it's oh so pretty low. Oh, la 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 la. Make a move from city to city, but I can't take it in, 'cause it's oh so pretty low. Oh, la 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 la. You can't bend light, 'cause you're so crystalline. From miles away, I can hear you breathing. Make a move from city to city, but I can't take it.
When using a Plinko board, to obtain the number of paths to each of the slots, and ultimately the probability of the marbles descending to one of the middle 7 columns, a Pascal's triangle with 13 rows is used. the probability that a marble starting in slot G will land in a particular slot can be computed using an argument based on the number of paths used. To determine the probability that multiple marbles will fall from slot G to the other various slots, the probability of one marble falling must firstly be computed. Looking at the last row and knowing the total number of rows is 13, n is therefore 12. The sum of entries can be found by 2 to the n power. So then the sum of the entries is 2 to the 12th power, which is 4096. This is the denominator of the probability fraction because there is at least one path that has a probability of 1 over 2 to the 12th power. To compute the numerators of the probability fraction, Pascal's triangle also comes in handy, as the last row of the triangle are the numerators for the probability of each column. Based on the theoretical probabilities calculated, the following observations can be made. Therefore, in order to find the probability of the marbles descending down the middle 7 columns, the probability that a marble will drop through each of the 7 slots needs to be added. So, the probability of the marble going through slot D, given that it started in slot G, through the probability of it going to slot J, given it started in slot G. So, when all of these are added, the total probability comes to 3,938 over 4,065, which is 96.14% of the marbles exiting one of the 7 slots at the bottom. So, if it takes 32 marbles to weigh down the cup catching the marbles at the bottom of the Planko board, the total number of marbles that need to be used must be also calculated. This can be found by having 32 divided by 3,938 over 4,065, or the probability of a marble falling through one of the 7 slots. This gives a number of marbles to 33.32. Therefore, 34 marbles must be used with the Planko board.
When a marble rolls down an inclined plane, it has both translational kinetic energy and rotational kinetic energy. So in order to calculate the velocity of the marble rolling down the plane, we can use the formula for translational kinetic energy and rotational kinetic energy. Translational kinetic energy is equal to 1/2 mass times velocity squared, and rotational kinetic energy is 1/2 the moment of inertia times omega squared. The moment of inertia describes how the mass is distributed in a round object. And for a solid sphere like a marble, it's equal to 2/5 the mass times the radius squared. Omega is the rate at which it rotates, which is equal to velocity divided by the radius. So, we can take this expression for total kinetic energy, set it equal to potential energy, which is the mass of the marble, times the acceleration due to gravity, times the height of the inclined plane. And then we can solve for V. This is the catapult we use in our Rube Goldberg machine. The projectile goes at this end and is anchored down by a string, and at this end there's a rubber band, and the tension in the rubber band provides the force to move the projectile. So in order to predict where the projectile lands, we have to first find the velocity of the marble as it leaves the catapult. And so first we have to calculate the potential energy stored in the system, which is equal to the force needed to hold this down in place times the stretch, so the height of the rubber band. So we use a spring scale to measure how much force it takes to hold this in starting position. And that's measured in newtons, the force, multiplied by the height of the rubber band, or how far it's stretched, which is in meters. Then we get Newton meters, which is also known as joules, and that tells us the potential energy. And we set the potential energy equal to roughly the kinetic energy, which is 1/2 mass times velocity squared. And we use that equation to solve for the velocity. The problem is that not all potential energy is transferred into kinetic energy. So when we launch the marble, some of that energy is used if the catapult moves back and forth after the projectile is launched, or as it's launching, it doesn't move perfectly in a straight line. Sometimes it shakes back and forth like this. And also there's sound energy. So a lot of these factors contribute to making the machine less efficient, and there's really no way to predict exactly how efficient it will be until we test it out. So first we have to test it and measure it, then find how efficient it is, and then make our predictions.